Well, hello guys, here Mr. Yi with another video for the grade 12. This time we're going to be answering question 9 from the mid-year diagnostic exam developed by Professor Rodriguez. And this question is quite interesting. It's a question about universal law of gravitation. It's a topic done in grade 11. The question says when the moon is in a third quarter phase, it forms a right angle triangle with the earth and the sun as shown below. And then you can see the sun, the moon, and the earth. The distance between the center of the earth and the moon is 3,84 times 10 to the 8 meters. Let's write it down here, the distance between the earth and the moon. So this distance here is 3,84 times 10 to the 8 meters. And the distance between the center of the moon and the sun is 1,5 times 10 to the 11 meters. The masses of the earth, moon and sun are, so the mass of the earth is given here and is going to be equal to, right here, mass of the earth is equal to 5,98 times 10 to the 24 kilograms. The mass of the moon is 7. Mass of moon is equal to 7,35 times 10 to the 22 kilograms, and the mass of the sun is equal to 1,99 times 10 to the 30 kilograms respectively. So you have all the data, you have all the masses, you have all the distance. And now question 9.1, state Newton's law of universal gravitation in words. So let's go to state Newton's law of universal gravitation in words. And the law of universal gravitation states that each object in the universe attracts every other object or body with a force that is directly proportional to the product of the masses. That side in symbol can say that the gravitational force, this attractive force, is going to be directly proportional to the product of the masses. This is in symbol, but you cannot say it in symbol, okay? And inversely proportional to the square of the distance between the centers. Here is that the gravitational force is inversely proportional to the square of the distance between the center. We can use small r or big R, it doesn't really matter. Let's write a big R here, square. And this is the universal law, or the law of universal gravitation in words. Question 9.2, calculate the magnitude of the net force on the moon due to the gravitational attraction of both the earth and the sun. Assume they are at right angle to each other. So exactly at right angle. Here we are, and we're going to do this one real fast, but let's do a small drawing here. Remember, all these objects are attracting each other, but we only worry about the moon. So the earth is going to pull the moon towards itself with this force here, towards itself here, with a force that I'm going to call Fe, force from the earth. And I'm going to move there. And now the sun is going to be pulling the moon towards itself, which is in this direction, with a force which I'm going to call Fs, force from the sun. So now where is the resultant force? They're asking you to calculate the net or resultant force in the question. Look down there. So where will the resultant force be? Well guys, this one will form a right angle triangle. If you do this one here and you use the tail to tail method to add the vectors, the resultant vector is going to be this line here. So this one is F net. Alright, now the question is, how do you calculate this F net? You have to use Pythagoras. Remember this one here, if I move it in this way, you can see it's a right angle triangle, in which this one here must go here, so you can see it. This is triangle at right angle. So all we have to do to calculate the F net, guys, F net square, let's take the symbol of the vector square is equal to fe square plus fs square. So we have to calculate fe and fs. All right, now those are very easy to calculate. All we have to do is to use the gravitational law formula, which is right here. That is the law of gravitation, universal gravitation, and the capital G is a constant and is going to be in this table of constant, as you can see there. So everything is given. All we're going to do now is to substitute. So the first thing we're going to do is to calculate the force that the Earth exerts on the moon. I'm going to call, or we did call already, Fe. This one is equal to the product of capital G, mass of the Earth, mass of the moon, divided by the distance squared, distance between the Earth and the moon. And guys, everything is given to us. It is in the picture, so we can come here and substitute. So the force of the Earth is going to be equal to, we get here that the force from the Earth on the moon is going to be equal to 1,99 times 10 to the 20 Newton. That is the force from the Earth. And now we have to do the same for the force that the sun exerts on the moon. Here you will get that the force from the sun is going to be equal to 4,34 times 10 to the 20 Newton. Okay guys, now when we have the mass from the Earth and the force from the Earth and the force from the sun, know that this is a 20 here, okay, be careful with that one. When we have that one, then we can use the Pythagoras here. So the force, the net force square is equal to the force from the Earth square plus the force from the sun square. Okay, that is the Pythagoras. Now here, if we use the square root, we get that the net force, I want to do everything at once, I want to struggle here. When you substitute, you get now the force from the Earth is 1,99 times 10 to the 20. Be careful with that one. I transfer wrong from the calculator. This one is to the power 2 plus the 4,34 times 10 to the 20 square. Alright, and this is the calculation we have to do now. Then you get that the net force, or the magnitude of the net force, is equal to 4,77 Newton, times 10 to the 20 Newton. There we go. This one is the answer for the net force that the Earth and the moon exert on the and the sun exert on the moon. Guys, this one is the final answer. And they say calculate the magnitude, so you don't have to calculate the direction there. Okay. Now question 9.3. After landing on Mars, an astronaut, Prof. Dioka, performed a simple experiment by dropping a rock. A quick calculation using the drop height and time of the fall. He found the acceleration of the rock to be 3,73 meters per second square. The Mars has a radius of 3,39 times 10 to the 6 meter. Calculate the mass. Guys, this one is quite simple. Let's quickly have to the data we have. We know that this one is question 9.3.1. Okay, they know that they give us the acceleration of the moon to be 3,73 meters per second square, and they gave us that Radius of the moon is given to us. The radius of the moon is 3,39 times 10 to the 6 meters. And they ask us to calculate the mass of Mars. Okay? That is what they ask us to calculate. So we have acceleration due to gravity, we have the radius, and we are looking for the mass. Now be careful, we are not looking for the mass of the rock, we're looking for the mass of Mars. Okay? So this mass here is for Mars. So make sure you don't get confused. So if you go to the formulas, what formula can we use here according to the data we have? Here it is, guys. Acceleration due to gravity is equal to g multiplied by the mass of the place divided by the distance squared. So that is the formula we are going to use here. So if we write the formula, g is equal to capital G mass of the planet divided by the radius of the planet to the power 2. When you substitute, you have 3,73 equal to 6,67 times 10 to the minus 11 multiplied by the mass of the planet we are looking for divided by the radius of the planet, which is given to us, and it's 3,39 times 10 to the 6 square. And guys, this one is once more simple calculations here. So I don't want to take long doing these calculations here, but when you do it, make sure you calculate it right, and then you will get that the mass of Mars is going to be 6,43 times 10 to the 23 kilograms. That is the mass of the moon, right? This is the answer for this question there. And that is the answer. So the final question say acceleration, calculate the acceleration of gravity due to Mars at a distance 2 times rm from the center of the planet. And guys, for this question we have to apply the same formula as we have right now, the same formulas we have here, but the only difference in the data, this one is 9.3.2 guys, the only difference is that the radius now, or the distance, is going to be equal to 2 times r, which r is going to be 3,39 times 10 to the 6. So that one changed. So you have to calculate the acceleration due to gravity. Same formula. This one is capital G mass of the planet. We did just calculate divided by the distance squared. Remember, this is the distance, so it's the radius times 2, because in this case it's 2 times the distance of the radius of the planet. So it's very simple. It's the same data, we just substitute. We're going to do that one real fast. So when we go here to the question, the acceleration due to gravity is equal to capital G multiplied by the mass of the planet divided by the distance squared. So if we do this one here real fast, is 6,67 times 10 to the minus 11 multiplied by the mass of the planet that we did calculate, 6,43 times 10 to the 24, 4 here, divided by 2 times the radius of the planet, which is 3,39 times 10 to the 6 everything squared. Guys, and the acceleration due to gravity on the planet is going to be equal to 0,93 meters per second squared. Now they asked to calculate acceleration, and acceleration have a direction, and the same as the acceleration due to gravity on the Earth is going to be towards the center of the planet, in this case is Mars. Guys, this is all for this question, this is all for the video. I hope it helped, I hope you understand. Thumb up, subscribe for the channel. I'll see you next time. Mr. G here.